When we talk about humans walking on two legs, it is tempting to imagine a dramatic moment when our ancestors suddenly stood up and changed forever. But evolution does not work that way. To understand how and why bipedalism began, we first need to understand what came before it. The story starts not with humans, but with an ancestor we no longer have, the last common ancestor shared by humans and chimpanzees. Most scientists agree that humans and chimpanzees split from a shared ancestral population somewhere between roughly 8 million and 6 million years ago. This split did not happen overnight, and it did not involve a single pair of individuals. It was a slow process spread across generations, as populations became separated and followed different evolutionary paths. One lineage would eventually lead to modern chimpanzees and bonobos. The other would give rise to hominins, the group that includes humans and our extinct relatives. The last common ancestor, often shortened to LCA by researchers, is not a species we have directly identified in the fossil record. Instead, it is a scientific reconstruction, built by comparing living apes with early fossil hominins and looking for shared traits. For decades, the dominant assumption was that this ancestor looked and moved much like a modern chimpanzee. That idea shaped early thinking about human evolution. Humans were seen as having evolved away from a knuckle-walking, tree-climbing ape. Over time, that view began to change. Modern chimpanzees and gorillas are highly specialized in their own ways. Chimpanzees are expert knuckle walkers on the ground and agile climbers in trees. Gorillas are adapted for powerful, weight-bearing knuckle walking and largely terrestrial lives. These specializations did not freeze in time after the split with humans. They evolved too. That realization forced scientists to reconsider a key question. If chimpanzees are highly specialized today, then the last common ancestor may not have moved exactly like them. Research over the past several decades suggests a different picture. Rather than a strict knuckle walker, the last common ancestor was likely a versatile climber that could also move on the ground in several ways. It probably spent a significant amount of time in trees, using strong arms and flexible shoulders to climb and hang. On the ground, it may have walked on all fours at times, stood upright occasionally, and moved in ways that do not fit neatly into modern categories. This matters because it changes how we think about the origins of bipedalism. If our ancestor already had the ability to stand upright for short periods, then walking on two legs did not require inventing an entirely new behavior. Instead, evolution could build on an existing capacity. One clue comes from anatomy shared across all great apes, including humans. Apes have highly mobile hip joints, flexible lower backs compared to many mammals, and shoulders adapted for a wide range of motion. These features are useful for climbing, but they also make upright posture possible. Even modern chimpanzees, despite being adapted for knuckle walking, can stand and walk upright for short distances. They do this when carrying food, displaying socially, or moving through shallow water. This tells us something important. Upright posture did not appear out of nowhere in the human lineage. It was already part of the primate toolkit. Fossils help refine this picture further. Although we do not have a confirmed fossil of the last common ancestor itself, we can bracket its characteristics by looking at both sides of the evolutionary split. Early hominins, such as Sahelanthropus from Central Africa and Orrorin from Kenya, show traits that hint at upright posture very early in the hominin line. Meanwhile, modern apes show what happens when evolution favors different solutions to survival challenges. The geographic setting also matters. Genetic evidence and fossil discoveries point to Africa as the homeland of this ancestral population. During the late Miocene epoch, roughly 10 million to 5 million years BCE, Africa was not a single uniform environment. It was a patchwork of forests, woodlands, river corridors, and more open areas. Climatic changes were gradually altering rainfall patterns and vegetation. Dense forests were shrinking in some regions, while more open habitats expanded. An animal living in such a mixed landscape would benefit from flexibility. Tree climbing would remain important for feeding and safety, but travelling between patches of forest or woodland would increasingly require movement on the ground. The last common ancestor was likely well suited to this kind of environment, not locked into one mode of movement, but capable of switching between several. This ecological flexibility helps explain why the hominin lineage did not begin with a sudden abandonment of trees. Instead, the earliest steps toward bipedalism likely occurred in a creature that was already comfortable both above and below the forest canopy. Another key piece of evidence comes from comparative muscle and skeletal studies. Humans retain muscles that are rarely used today, but are well developed in climbing apes. For example, certain shoulder and forearm muscles reflect a climbing past. These traits are evolutionary leftovers, suggesting that our ancestors spent significant time in trees long before bipedal walking became dominant. At the same time, humans lack some features that define specialized knuckle walkers. The structure of the human wrist, for example, does not show the locking mechanisms seen in chimpanzees and gorillas that protect the joint during knuckle walking. This absence suggests that our lineage did not pass through a long phase of specialized knuckle walking. Instead, our ancestors likely retained a more generalized form of quadrupedal movement when on the ground. Scientists such as C. Owen Lovejoy have argued that this generalized ancestor already stood upright more often than previously assumed. Lovejoy and others have emphasized that bipedalism did not evolve from a body plan identical to that of modern chimpanzees. While not all researchers agree on every detail, there is broad consensus that the last common ancestor was not simply a chimpanzee-like ape frozen in time. To understand why upright walking began to matter, we have to step away from bones and muscles and look at the world those bodies move through. This shift toward bipedalism did not happen in isolation. It unfolded against a backdrop of slow but profound environmental change, especially in Africa, where the human lineage took shape. Between roughly 10 million and 5 million years ago, Africa was undergoing a long period of climatic instability. This was not a single event, but a series of overlapping trends driven by global cooling, shifting ocean currents, and tectonic activity. Together, these forces altered rainfall patterns, vegetation, and the structure of entire ecosystems. For animals living there, including early hominins, the ground beneath their feet was quite literally changing. Earlier in the Miocene epoch, much of equatorial Africa was covered by dense forests. These environments favoured animals that could climb, swing, and move efficiently through trees. As time passed, global temperatures declined and seasonal variation increased. Rainfall became less predictable. Forests began to fragment, breaking into patches separated by open woodland, scrub, and grassy areas. This process did not turn Africa into endless grassland overnight. Instead, it created what scientists call mosaic environments. In these landscapes, forested areas existed alongside more open spaces, sometimes only a short distance apart. River corridors, lake shores, and upland woodlands formed a complex patchwork rather than a single dominant habitat. One of the major drivers of this change was the formation and expansion of the East African Rift System. As tectonic plates slowly pulled apart, the land fractured and uplifted, creating valleys, highlands, and volcanic activity across eastern Africa. These geological shifts altered local climates by changing wind patterns and rainfall distribution. Regions that once received consistent moisture became drier, while others experienced stronger seasonal swings. The rift also created new ecological opportunities. Lakes formed in rift valleys, supporting diverse plant and animal life. At the same time, uplands cast rain shadows, reducing precipitation in some areas and encouraging the spread of grasses adapted to drier conditions. Fossil pollen, soil chemistry, and isotopic data from ancient sediments all point to increasing environmental variability during this period. Why does this matter for the story of bipedalism? In a stable, dense forest, there is little incentive to move long distances on the ground. Food is often available in trees, and climbing offers safety from predators. In a mosaic environment, resources are scattered. Fruit trees may be abundant in one patch and scarce in another. Water sources may shift seasonally. Animals that can travel efficiently between these patches gain an advantage. For an ape-like creature already capable of climbing an occasional upright posture, this new landscape posed both a challenge and an opportunity. Moving between patches meant spending more time on the ground. Doing so safely and efficiently became increasingly important. Upright walking, even if imperfect, could help meet that need. Standing upright changes how an animal interacts with its environment. It raises the head, improving the ability to see over tall grasses or low shrubs. It frees the hands, allowing food to be carried from one place to another. It can reduce the surface area exposed to direct sunlight during the hottest parts of the day, potentially aiding in temperature regulation. None of these benefits alone explains bipedalism, but in combination, they become more meaningful in open or semi-open settings. Evidence for these environmental changes comes from multiple sources. Fossilized plant remains show a gradual increase in grasses that use a photosynthetic pathway adapted to dry, open conditions. Soil carbonates preserve chemical signatures that reflect the types of plants growing nearby. Animal fossils reveal shifts in herbivore communities, with more species adapted to grazing and mixed feeding appearing over time. Importantly, these changes did not eliminate forests. Instead, they made forest resources less continuous. For early hominins, this meant balancing life in the trees with increasing demands on the ground. Selection favored individuals who could navigate both worlds. The timing of these environmental shifts aligns closely with the earliest known hominin fossils. Species such as Sahelanthropus and Aurorin appear during periods when habitats were becoming more variable. This does not prove causation on its own, but the correlation is striking. Upright posture begins to appear not in a world of unbroken forest, but in one defined by ecological uncertainty. This uncertainty also affected food availability. Seasonal environments produce seasonal shortages. When preferred foods disappear for part of the year, flexibility becomes critical. An animal that can travel farther with less energy, carry food, or exploit a wider range of resources has a better chance of survival and reproduction. Over generations, even small advantages can shape anatomy and behavior. With the environmental stage set, the story now turns to physical evidence. The shift toward bipedalism did not announce itself clearly or all at once. Instead, it appears in the fossil record as a series of subtle clues. Fragments of skulls, pieces of leg bones, isolated teeth, each offering a partial glimpse into how early members of the human lineage were beginning to move. These fossils come from a narrow but crucial window in time, roughly between 7 million and 6 million years BCE. This is the period closest to the evolutionary split between humans and chimpanzees, making it one of the most important and controversial phases in human origins. The remains are rare, incomplete, and often debated, but they represent the earliest physical hints that upright posture was beginning to matter. One of the most discussed finds from this era is Sahelanthropus chadensis, discovered in the early 2000s in what is now Chad, in Central Africa. This location alone challenged long-held assumptions. For decades, many researchers focused almost entirely on Eastern Africa as the cradle of human evolution. Sahelanthropus suggested that early hominins may have been spread across a much wider area. The most famous fossil of Sahelanthropus is a partial skull, often called Tumai by the research team led by Michel Brunet. At first glance, the skull looks small-brained and ape-like. Its cranial capacity falls within the range of modern chimpanzees. But one feature drew immediate attention: the position of the foramen magnum, the hole at the base of the skull through which the spinal cord passes. In animals that move primarily on all fours, this opening sits toward the back of the skull, aligning the head with a horizontal spine. In bipeds, it is positioned more centrally underneath the skull, allowing the head to balance atop an upright posvenochnik. In Sahelanthropus, the foramen magnum appears to be placed farther forward than in modern apes. Why does this matter? Because head balance is not a trivial detail. Holding the head upright without excessive muscular effort is a key requirement for habitual bipedal posture. If Sahelanthropus regularly held its head over an upright spine, it suggests that standing or walking upright was not unusual behavior. Not everyone agrees on this interpretation. The fossil is distorted, and reconstruction involves some uncertainty. Critics argue that the skull alone cannot prove habitual bipedalism. Still, even cautious researchers acknowledge that Sahelanthropus does not fit neatly into the anatomy of modern African apes. A second important fossil comes from Eastern Africa, Orrorin tuganensis, discovered in Kenya and described by a team led by Brigitte Senut and Martin Pickford. Unlike Sahelanthropus, Orrorin is represented not only by dental remains but also by fragments of the femur, or thigh bone. The femur is especially informative when studying locomotion. In bipeds, it bears weight differently than in quadrupeds. The distribution of bone tissue, the shape of the neck connecting the shaft to the hip, and the internal structure all reflect how forces pass through the leg during movement. The femur fragments attributed to Orrorin show patterns more consistent with upright weight-bearing than with knuckle walking or climbing alone. The thickness of the bone beneath the neck suggests that stress was transmitted in a way similar to later hominins. This has led some researchers to argue that Orrorin was already spending significant time walking upright on the ground. At the same time, other parts of the skeleton, including curved finger bones, indicate strong climbing abilities. This combination reinforces an emerging theme. Early hominins were not abandoning trees, but they were beginning to integrate upright posture into their daily lives. A third early contender is Ardipithecus cadaver, known from fragmentary remains found in Ethiopia, and dated slightly later than Sahelanthropus and Orrorin. While more limited in scope, these fossils include a toe bone that suggests reduced grasping compared to modern apes. This hints at a foot beginning to adapt for ground-based movement, even if climbing remained important. Taken together, these fossils do not give us a single, clear picture of the first biped. Instead, they show variation. Different populations experimented in evolutionary terms with different balances between climbing and upright walking. This is exactly what we would expect during the early stages of a major transition. What is striking is how early these hints appear. Upright-related traits show up very close to the time of the human-chimpanzee split. This challenges older models that place the origin of bipedalism much later, after other human-like traits had already evolved. Instead, bipedal tendencies may have been among the earliest defining features of the hominin lineage. It is also important to note what these early fossils do not show. None of them displays the full suite of adaptations seen in later, fully bipedal hominins. Their feet were not built like ours. Their hips were not yet optimized for long-distance walking. Their upper bodies still bore the marks of a life spent climbing. This tells us that bipedalism did not begin as an all-or-nothing change. It emerged as a partial solution to new challenges, layered onto an existing body plan. Early hominins could move upright when it was useful, and revert to climbing when necessary. By the time Australopithecus appears in the fossil record, the story of bipedalism becomes clearer and more grounded in evidence. Unlike the earlier hints offered by Sahelanthropus and Aurorin, Australopithecus provides a richer anatomical record. This allows scientists to move beyond isolated clues and begin reconstructing how an early hominin actually lived and moved. Australopithecus lived between roughly 5.8 million and 4.4 million years BCE, primarily in what is now Ethiopia. The most well-known species, Australopithecus ramidus, was unveiled to the scientific world after more than a decade of careful study led by Tim White and an international research team. The fossils were fragmentary and fragile, but together they formed one of the most important discoveries in the study of human origins. What makes Australopithecus so significant is not that it was fully bipedal. It was not. Instead, its importance lies in how clearly it demonstrates a transitional stage, a creature that could walk upright on the ground while still being highly adapted for life in the trees. The environment Australopithecus inhabited helps explain this balance. Evidence from fossil plants, animals, and soil chemistry shows that Australopithecus lived in woodland habitats rather than open grasslands. These were areas with substantial tree cover, mixed with open spaces, similar to modern African woodlands. This directly challenged the long-standing savanna hypothesis, which argued that bipedalism evolved primarily as an adaptation to open grasslands. Australopithecus shows that upright walking did not require a treeless landscape. Instead, bipedalism began in environments where climbing still mattered, but ground travel was becoming increasingly important. The skeleton of Australopithecus ramidus reveals this dual lifestyle in remarkable detail. Its pelvis is especially revealing. The upper part of the pelvis is shortened and broadened compared to that of modern apes. This shape helps stabilize the body during upright walking, preventing it from tipping side to side with each step. At the same time, the lower pelvis retains features suited for powerful climbing muscles. This combination tells us something crucial. Selection was acting on the body to improve upright walking, but not at the expense of climbing ability. Australopithecus did not simply stand up and abandon the trees. Instead, it carried two different locomotor strategies in one body. The legs of Australopithecus also reflect this compromise. While not as long or as specialized as those of later hominins, they show adaptations consistent with weight-bearing on two limbs. The knee joint in particular suggests that the animal could straighten its leg fully while standing, a requirement for efficient upright posture. The foot, however, may be the most striking example of Australopithecus's unique position in human evolution. Unlike modern humans, Australopithecus retained a grasping big toe that could oppose the other toes, much like a hand. This made climbing branches easier and safer, yet the rest of the foot shows signs of rigidity that would have helped during walking on the ground. This is not a foot built for running long distances. It is a foot designed for careful movement, climbing, balancing, and walking upright when needed. Once again, the message is clear. Bipedalism was emerging gradually, layered onto an older way of life rather than replacing it. The upper body of Australopithecus reinforces this picture. Its arms were long and strong, well suited for climbing. The shoulder joint allowed a wide range of motion, similar to that seen in modern apes. Importantly, the wrists lack the structural reinforcements associated with knuckle walking. This supports the growing consensus that the human lineage did not pass through a knuckle-walking stage like that of chimpanzees and gorillas. In other words, Australopithecus was not an ape that had stopped knuckle-walking. It was an animal that never specialized in it in the first place. The skull and teeth of Australopithecus add further context. The brain was small, comparable in size to that of modern chimpanzees. There is no evidence of advanced cognition or complex tool use at this stage. However, the teeth show reduced canine size compared to many apes. This reduction suggests changes in social behavior, possibly involving less male-to-male aggression. Why does this matter for bipedalism? Because social structure influences movement and behavior. Reduced reliance on physical intimidation may have favored other strategies, such as cooperation or food sharing. Upright posture could have played a role here by making carrying and sharing food more practical. Tim White famously described Australopithecus as revealing a creature very different from what we expected. It was not a chimp-like ape inching toward humanity. It was something more complex and more informative, a reminder that evolution does not move along a straight line toward a known outcome. By the time Australopithecus was walking upright on the ground some of the time, a crucial question comes into focus. If early hominins could already survive by climbing and moving on all fours when needed, why did natural selection continue to favor upright posture? What made standing and walking on two legs worth refining generation after generation? There is no single answer. Instead, bipedalism appears to be the result of multiple pressures acting together over long periods of time. Each pressure on its own might seem modest. Combined, they gradually tip the balance in favor of upright walking. One of the most widely discussed factors is energy efficiency. Moving across the ground costs energy, and animals that spend less energy getting from one food source to another gain a survival advantage. Studies of human walking compared to chimpanzee quadrupedal movement show that upright walking, once properly adapted, can be surprisingly efficient over long distances. For early hominins living in mosaic environments, food was not evenly distributed. Fruit trees, tubers, seeds, and scavenging opportunities were scattered across the landscape. Individuals who could travel between these patches using less energy could forage more effectively and recover faster. Even small improvements in efficiency, repeated over thousands of generations, would matter. Importantly, this advantage would not have appeared instantly. Early bipedalism was likely awkward and imperfect, but natural selection does not require perfection. It favors improvement. Any anatomical change that made upright walking slightly less costly would be preserved and built upon. Another pressure involves feeding behavior. Upright posture allows an individual to reach food that is otherwise out of reach. Standing on two legs makes it easier to pull down branches, gather fruit, or feed from shrubs and small trees without climbing fully into them. This behavior is seen today in chimpanzees, which often stand upright briefly while feeding. In environments where trees were spaced farther apart or food was available at different heights, the ability to stand while feeding would have been useful. Over time, frequent use of upright posture during feeding could reinforce anatomical changes that made standing easier and more stable. Carrying is another critical factor. Walking on two legs frees the hands. This may sound obvious, but its implications are profound. Early hominins that could carry food, tools, or infants had more options available to them. Carrying food allows individuals to transport resources from where they are found to safer or more social locations. This could support food sharing, reduce competition at feeding sites, and strengthen social bonds. Carrying infants would reduce the need to leave vulnerable young behind while foraging, increasing offspring survival. At this early stage, there is no evidence for complex tools or planned transport over long distances, but even simple carrying, repeated daily, would favour individuals comfortable moving upright for extended periods. Visibility also played a role. In landscapes with tall grasses, shrubs, and uneven terrain, standing upright improves the ability to see both resources and threats. A taller posture allows an individual to spot predators earlier, assess the movement of other group members, and navigate the landscape more effectively. This advantage would have been especially relevant during travel between habitat patches. Upright posture does not eliminate danger, but it changes how danger is perceived and responded to. Early detection can mean the difference between escape and ambush. Temperature regulation is another pressure often discussed. Upright posture reduces the amount of body surface exposed to direct midday sunlight and increases exposure to cooling breezes. In warmer, more open environments, this can help prevent overheating. While this factor alone does not explain the origin of bipedalism, it may have reinforced its value once early hominins began spending more time on the ground. As environments became more seasonally dry and hot, the ability to manage body heat would grow in importance. Social behavior adds yet another layer. Standing upright changes how individuals interact visually. It makes gestures more visible and displays more prominent. Upright posture can signal status, intention, or alertness. In many primate species, posture plays a role in communication, dominance, and coordination. Reduced canine size in early hominins suggests changes in social structure, possibly involving less reliance on physical aggression. In such contexts, posture and gesture may have taken on greater importance. Upright stance could enhance social signaling without requiring violence. With the appearance of Australopithecus, bipedalism crosses an important threshold. No longer an occasional behaviour layered onto a climbing lifestyle, upright walking now becomes habitual. This does not mean that Australopithecus walked exactly like modern humans, nor that trees disappeared from its life. But it does mean that natural selection had begun to reshape the body in ways that clearly favoured regular movement on two legs. Australopithecus lived between roughly 4.2 million and 3 million years BCE, with fossils found across eastern and southern Africa. This wider geographic spread alone signals something new. A lineage dependent on habitual upright walking could move across varied landscapes more effectively, expanding into regions that earlier hominins may not have occupied as successfully. One of the earlier species, Australopithecus anamensis, provides some of the first clear skeletal evidence of this shift. Fossils from Kenya and Ethiopia include parts of the tibia, the shin bone, which show adaptations for bearing weight in an upright stance. The shape of the ankle joint suggests stability when the leg is extended vertically, a key requirement for walking on two legs repeatedly and safely. Soon after, Australopithecus afarensis appears, the species best known through the famous partial skeleton nicknamed Lucy. Discovered in Ethiopia and dated to around 3.2 million years BCE, Lucy transformed scientific understanding of early human locomotion. Although only about 40% complete, her skeleton revealed a creature unmistakably adapted for bipedal walking. Lucy's pelvis is shorter and broader than that of earlier hominins like Australopithecus. This shape helps support the organs during upright walking and stabilizes the trunk over the hips. The femur angles inward from the hip to the knee, creating what is known as a valgus angle. This alignment positions the feet closer to the body's center of gravity, reducing side-to-side sway while walking. These features are not incidental. They are precisely the traits needed for habitual bipedal locomotion. Lucy was not simply capable of standing upright. Her body was built to do so again and again. At the same time, Australopithecus retains some primitive traits. The arms are long relative to the legs, and the fingers are curved, indicating that climbing still played a role in daily life. This combination confirms that habitual bipedalism did not require abandoning the trees entirely. Instead, it reflects a body optimized for walking on the ground while still capable of climbing when necessary. What changes with Australopithecus is frequency and reliance. Upright walking was no longer just useful in certain moments. It had become the primary way of moving from place to place on the ground. This shift is also visible in the foot. While Australopithecus does not have the fully arched foot of modern humans, it shows a more rigid structure than that of Ardipithecus. The big toe is aligned more closely with the other toes, improving push-off during walking. This alignment reduces grasping ability but increases efficiency and stability on the ground. Such changes reflect a clear trade-off. Australopithecus was sacrificing some climbing efficiency in exchange for better terrestrial movement. Natural selection was beginning to favour walking over climbing as the default mode of travel. The environment helps explain why this trade-off made sense. By this time, African landscapes continued to be variable and patchy. Woodland and open areas existed side by side and resources were scattered. Habitual upright walking made it easier to move between these patches, carry food, and navigate seasonal changes. Dietary evidence supports this picture. Tooth enamel studies suggest that Australopithecus had a flexible diet, including fruits, leaves, and tougher plant materials. Foraging for such resources would have involved both ground-based searching and reaching into shrubs and low trees. Upright posture would have been useful in both contexts. Bones can suggest how an animal moved, but footprints show movement itself. With the discovery of the Laetoli footprints, bipedalism is no longer inferred only from anatomy. It is observed directly, captured in a brief moment when early hominins walked across a soft surface and left behind a record that would endure for millions of years. The Laetoli site lies in northern Tanzania, in a region shaped by volcanic activity. During the time of Australopithecus afarensis, nearby volcanoes periodically spread fine ash across the landscape. On one such occasion, light rain fell onto freshly deposited ash, creating a damp, powdery surface. Shortly afterward, a small group of hominins walked across it. More ash soon followed, sealing the impressions and preserving them. The footprints were discovered in the late 1970s by a research team led by Mary Leakey, one of the most influential paleoanthropologists of the 20th century. At first, they were not immediately recognized as hominin. Only after careful excavation did their true significance become clear. What the researchers uncovered was a trail extending for several dozen meters, consisting of clear, repeated footprints made by at least 2 individuals and possibly a third. The spacing, depth, and shape of the prints offered something extraordinary, a direct snapshot of how early hominins walked. The most striking feature of the Laetoli footprints is their unmistakably bipedal pattern. Each footprint shows a heel strike followed by weight transfer along the sole and push-off from the front of the foot. This sequence is characteristic of upright walking. There are no signs of knuckle impressions, tail marks, or other indicators of quadrupedal movement. Even more telling is the position of the big toe. In modern apes that retain grasping feet, the big toe angles outward. In the Laetoli prints, the big toe is aligned closely with the other toes pointing forward. This alignment improves balance and efficiency during walking and is a key feature of habitual bipedalism. The footprints also show evidence of an arch-like structure in the foot, although not as pronounced as in modern humans. This suggests a foot capable of absorbing shock and supporting body weight during upright movement. Combined with earlier skeletal evidence, the footprints confirm that Australopithecus afarensis walked on 2 legs regularly and confidently. What makes Laetoli especially powerful is that it captures behavior, not just anatomy. Skeletons tell us what was possible. Footprints tell us what actually happened. These individuals were not posing upright for a moment. They were walking across the landscape in a natural, unremarkable way, so ordinary that it left no sign of hesitation or instability. The spacing between the footprints reveals something about body size and group composition. One set of prints is noticeably larger than the other. This size difference has been interpreted by some researchers as evidence of sexual dimorphism, with a larger individual walking alongside a smaller one. Others suggest the presence of a third individual whose prints overlap with the others. Regardless of the exact number, the scene implies social movement. These hominins were not alone. They were travelling together, possibly as part of a group, across an open area. This reinforces the idea that habitual bipedalism supported group mobility and coordination. The direction and pace of the footprints suggest steady walking rather than running or hurried movement. There are no signs of slipping, stumbling, or sudden changes in direction. The walkers appear relaxed and balanced. This is important because it indicates that upright walking was not an awkward or risky activity for them. It was normal. Mary Leakey herself emphasized this point, noting that the footprints looked so human in their pattern of movement. While Australopithecus afarensis was not human in many respects, its way of walking already shared key characteristics with ours. The Laetoli footprints also help resolve debates about timing. Before their discovery, some researchers questioned whether Australopithecus was truly a habitual biped or merely capable of upright walking. The footprints settle this issue decisively. By this time, bipedalism was not occasional. It was the default mode of terrestrial locomotion. This does not mean that Australopithecus walked exactly like modern humans. Subtle differences in stride length and foot pressure suggest variations in gait. The hips and legs were still shaped differently, and energy efficiency was likely lower than in later hominins. But the fundamental pattern was in place. By the time Australopithecus was leaving footprints at Laetoli, walking on 2 legs was no longer a novelty. But walking upright does not automatically mean walking efficiently or comfortably by modern standards. The next step in understanding bipedalism is not whether early hominins walked on 2 legs, but how they did it. This is where biomechanics enters the story. By studying fossil bones in detail and comparing them with the skeletons of modern humans and apes, scientists can reconstruct how forces move through the body during walking. These reconstructions reveal that Australopithecus walked upright in a way that was recognizably bipedal, but still different from us in important ways. One of the key differences lies in the pelvis. In modern humans, the pelvis is shaped like a bowl, with flared blades that support the organs and anchor muscles critical for balance during walking. Australopithecus had a shortened and broadened pelvis compared to earlier hominins, but it was still not identical to ours. This matters because of how balance works during bipedal walking. Each step requires the body to balance on one leg while the other swings forward. In modern humans, specialized hip muscles stabilize the pelvis, preventing it from tilting dangerously from side to side. Australopithecus possessed these muscles in a more developed form than earlier hominins, but they're not as refined as in later Homo. As a result, Australopithecus likely walked with a slightly different rhythm and posture. Computer models and fossil reconstructions suggest a gait that was upright but less smooth, with shorter strides and greater energy cost per step. The legs tell a similar story. Australopithecus had relatively long arms and shorter legs compared to modern humans. Longer legs increase stride length and improve walking efficiency over long distances. Shorter legs, by contrast, require more steps to cover the same ground. This does not mean Australopithecus was poorly adapted. It means that natural selection had solved the basic problem of upright walking, but had not yet optimized it for endurance travel. Walking worked, but it was not yet cheap. The knee joint provides another clue. In modern humans, the knee locks into a stable position when fully extended, allowing us to stand upright with minimal muscular effort. Australopithecus knees show partial adaptation toward this mechanism, but not to the same degree. Standing and walking would have required more constant muscular engagement. The foot, as hinted by the Laetoli footprints, was also in transition. Australopithecus lacked the fully developed longitudinal arch seen in modern humans. This arch acts like a spring, storing and releasing energy with each step. Without it, walking becomes less efficient and more tiring. Instead, the Australopithecus foot was flatter and more flexible. This made it less effective for long-distance walking, but still serviceable for shorter movements between feeding sites. It also retained some ability to adapt to uneven terrain, which would have been useful in woodland environments. Taken together, these traits point to a form of bipedalism that was functional but limited. Australopithecus could walk upright reliably, but not with the speed, efficiency, or endurance of later humans. This raises an important evolutionary question. If walking was still costly and imperfect, why did it persist? The answer lies in relative advantage. Even an inefficient bipedal gait may have been better than the alternatives available at the time. Quadrupedal walking on the ground, especially without specialized knuckle walking adaptations, would have been slower and less stable. Climbing down from trees to travel between patches would have required frequent transitions between modes of movement. Upright walking, even if imperfect, provided a consistent and adaptable solution. It is also important to remember that Australopithecus was not walking marathon distances. Daily movement likely involved short to moderate trips, frequent stops, and mixed use of ground and trees. In this context, extreme efficiency was less critical than versatility. Another insight comes from variation within Australopithecus itself. Different individuals and species show slightly different proportions and joint shapes. This suggests that bipedal gait was still under evolutionary experimentation. Natural selection was refining the system, testing different anatomical combinations. By this stage in the story, one fact is clear. Walking on two legs had become a defining feature of the human lineage. Yet it is just as important to understand what bipedalism did not immediately replace. Early hominins did not step fully into a new terrestrial world and leave the trees behind. Instead, they lived at the intersection of two worlds, and their bodies carried the marks of that compromise. Australopithecus and its close relatives were habitual bipeds on the ground, but they were also capable climbers. This was not a contradiction. It was an evolutionary trade-off, shaped by the demands of survival in landscapes that still made trees valuable. Evidence for continued climbing comes primarily from the upper body. The shoulders of Australopithecus were positioned higher and more forward than in modern humans. This orientation allows the arms to be raised above the head with ease, a crucial ability for climbing and hanging. In contrast, modern human shoulders are positioned lower and oriented more to the side, favouring throwing and manipulation rather than vertical climbing. The arms themselves were relatively long compared to the legs. Long arms increase reach and leverage when moving through branches, grasping trunks, or pulling the body upward. This proportion is inefficient for long-distance walking, but highly effective for climbing. Natural selection had not shortened the arms because climbing still mattered. The hands tell a similar story. Australopithecus fingers were curved, not straight like those of modern humans. Curved fingers are better suited for grasping branches and supporting body weight during suspension. This curvature develops through repeated use during life, but its presence in fossils indicates an inherited adaptation, not just individual habit. The wrist and elbow joints also retained flexibility suited to climbing. Unlike later Homo species, Australopithecus did not show full commitment to an upper body optimized for tool use or throwing. The anatomy suggests strength and mobility rather than precision and endurance. Why maintain these climbing traits if bipedalism was already established? The answer lies in risk and reward. Trees still offered safety. Predators such as large cats and hyenas were common in African environments. Climbing provided an escape route that ground-based movement could not always offer. Sleeping in trees likely reduced the risk of nocturnal predation, especially for smaller-bodied hominins. Trees also remained an important food source. Fruits, leaves, and other plant resources were often more abundant or predictable above ground. During certain seasons, climbing may have been the most reliable way to feed. A hominin that lost climbing ability too quickly would have been at a disadvantage. This is the heart of the trade-off. Improving walking efficiency on the ground often comes at the cost of climbing performance. Narrower hips, shorter arms, and stiffer shoulders help walking but hinder climbing. Early hominins could not afford to give up one strategy entirely in favour of the other. As a result, natural selection favoured compromise rather than specialisation. Australopithecus bodies were good enough at both walking and climbing, even if they were not perfect at either. This compromise also explains why bipedalism progressed slowly. Evolution does not push traits to extremes unless the environment strongly demands it. As long as trees remained valuable, there was little pressure to abandon climbing completely. Upright walking improved gradually, while climbing ability declined just as gradually. Importantly, this pattern challenges a simple narrative of progress. It is tempting to see bipedalism as a straight line toward modern human movement, with each step being an improvement. In reality, early hominin evolution involved balancing competing needs, not marching toward a predetermined goal. Different Australopithecus species show slightly different balances in this trade-off. Some appear to have retained more climbing ability than others. This suggests that local environments mattered. Populations living in more wooded regions likely climbed more often, while those in more open areas relied more heavily on walking. This variation also helps explain why multiple hominin species could exist at the same time. They were not all doing the same thing. Some leaned more toward terrestrial foraging, others toward arboreal feeding, even though all were bipedal on the ground. From a mechanical perspective, this mixed lifestyle placed unique stresses on the body. Joints had to accommodate both upright walking and climbing. Muscles had to support different patterns of movement. These competing demands may have limited how far any one adaptation could go at this stage. Once upright, walking became habitual. It did more than change how early hominins moved. It quietly transformed how they ate. Locomotion and diet are deeply connected in evolution, because how an animal moves determines where it can go, what it can reach, and what it can afford to spend energy on. With bipedalism firmly established, early hominins began to interact with food in new ways. Australopithecus did not suddenly become hunters or abandon plant-based diets. Instead, habitual walking expanded the range of edible options and altered foraging strategies in subtle but important ways. This shift marks a new phase in the story, where movement on two legs begins to reshape daily survival. One of the clearest changes is increased access to ground-based foods. Before habitual bipedalism, foraging was heavily tied to trees and shrubs. Fruits, leaves, and flowers were often gathered above ground, and travel between feeding sites relied on climbing and short ground movements. Upright walking made longer ground-based foraging trips more practical. This mattered because many nutritious foods are found at ground level. Tubers, roots, bulbs, and fallen seeds are calorie-rich, but often scattered and seasonal. Extracting them requires searching, digging, and carrying. An upright posture frees the hands for these tasks and allows individuals to transport food away from the point of discovery. Dental evidence supports this shift. The teeth of Australopithecus show thick enamel, well suited for processing hard or abrasive foods. This suggests a diet that included tougher plant materials than those favoured by many forest-dwelling apes. Such foods would have been especially valuable during dry seasons when soft fruits were scarce. Stable isotope studies of fossil teeth provide further insight. These chemical signatures indicate that Australopithecus consumed a mix of foods from both woodland and more open environments. This flexibility aligns closely with habitual bipedal movement, which allowed individuals to exploit a wider range of habitats. Walking upright also changed how food could be shared. Carrying allows individuals to move food from where it is found to safer or more central locations. This reduces feeding competition and may support social cooperation. While there is no direct evidence of structured food sharing at this stage, the physical ability to carry food creates the conditions for it to emerge. Even small-scale carrying can influence social behavior. A parent transporting food to offspring, or an individual bringing resources back to a group, changes patterns of interaction. Over time, these behaviors can shape selection pressures on anatomy and cognition. Another important dietary shift involves scavenging. There is ongoing debate about how early hominins accessed animal protein. Clear evidence for systematic hunting appears much later, but opportunistic scavenging likely began earlier. Upright walking would have made it easier to travel to carcasses, monitor predator activity from a distance, and carry pieces of meat or marrow-rich bones. Standing upright also improves visual scanning, which is crucial when navigating landscapes shared with predators. The ability to see over grasses and shrubs helps identify both food opportunities and dangers. This advantage becomes especially important when foraging on the ground. Importantly, increased access to diverse foods does not imply immediate dietary specialization. Australopithecus remained a generalist. Its success lay in flexibility rather than reliance on a single food source. Habitual bipedalism supported this flexibility by making it easier to move between different foraging zones. Energy economics plays a central role here. Walking on two legs, even if not yet fully efficient, allowed early hominins to cover more ground than climbing alone would permit. This increased foraging radius could offset the energy costs of walking, especially when high-value foods were obtained. Cause and effect reinforce each other in this process. As bipedal walking made new foods accessible, selection favoured individuals who could exploit those foods effectively. As diets broadened, movement strategies that supported that breadth became more valuable. Over time, anatomy, behaviour and environment became tightly linked. The impact of diet on teeth and jaws also hints at evolutionary branching. Some hominin lineages began to emphasise powerful chewing adaptations, while others maintained more generalised feeding strategies. These differences would later define separate evolutionary paths, even though all remained bipedal. It is also important to clarify what did not happen. Upright walking did not immediately lead to cooking, complex tools, or large brains. Those developments came much later. At this stage, the dietary impact of bipedalism was practical and ecological, not technological. By the time upright walking had become firmly established, evolution began to explore different ways of surviving with that body plan. Bipedalism did not force all hominins down a single path. Instead, it became a shared foundation upon which very different strategies could be built. One of the most striking examples of this diversity is found in the robust hominins, often grouped under the genus Paranthropus. Paranthropus appears after Australopithecus and overlaps with early members of the genus Homo. These hominins were fully bipedal, moving upright across the landscape much like their relatives. Yet everything above the neck tells a different story. Their evolution focused not on mobility or flexibility, but on feeding power. The first widely recognized species in this group is Paranthropus aethiopicus, known from eastern Africa. Later forms include Paranthropus boisei in eastern Africa and Paranthropus robustus in southern Africa. Together, they represent a long-running evolutionary experiment that lasted for more than 1 million years. What defines these hominins is not how they walked, but how they ate. Paranthropus species possessed massive jaws, extremely large molar teeth, and thick tooth enamel. Their skulls often featured a sagittal crest, a ridge of bone running along the top of the skull that anchored powerful chewing muscles. These features indicate an ability to process hard, fibrous, or abrasive foods with great force. This anatomy suggests a dietary specialization unlike that of Australopithecus. While earlier hominins were dietary generalists, Paranthropus appears to have focused heavily on tough plant foods, such as roots, tubers, sedges, and possibly hard seeds. These foods are abundant in some environments but require significant chewing power to exploit. Why does this matter for the story of bipedalism? Because it shows that upright walking was not tied to one specific ecological role. Paranthropus did not become bipedal in order to range widely, chase prey, or develop complex tools. It was already bipedal when its lineage doubled down on a feeding strategy that emphasized strength over versatility. The postcranial skeleton of Paranthropus confirms this. From the neck down, these hominins look very similar to Australopithecus. Their hips, legs, and feet show clear adaptations for habitual upright walking. There is no evidence that they reverted to quadrupedalism or relied more heavily on climbing than their ancestors. In other words, bipedalism had become evolutionarily fixed. Even when natural selection pushed head and jaw anatomy in extreme directions, walking on two legs remained unchanged. This has important implications for cause and effect. It tells us that bipedalism was no longer an experiment at risk of reversal. It was the baseline condition of the hominin lineage. Once established, it became the platform on which other adaptations evolved. Paranthropus also helps clarify the role of environment in shaping evolutionary paths. These hominins lived during a period of increasing climatic variability, with cycles of wet and dry conditions. In such settings, hard and fibrous plant foods can serve as reliable fallback resources when preferred foods are scarce. By specializing in chewing power, Paranthropus may have carved out a stable niche. Their anatomy suggests survival through strength rather than flexibility. This strategy worked for a long time, as evidenced by their persistence across different regions and environments. However, specialization comes with costs. While Paranthropus could process tough foods exceptionally well, their extreme cranial adaptations may have limited dietary flexibility. Their teeth and jaws were superb for certain foods, but less suited for others. This specialization may have made them vulnerable when environments changed in ways that reduced the availability of their preferred resources. In contrast, other hominins were beginning to explore different solutions. The coexistence of Paranthropus with early Homo species is especially revealing. Both groups were bipedal, both lived in overlapping regions. Yet they pursued very different survival strategies. One emphasized chewing strength and dietary specialization. The other would increasingly emphasize behavioral flexibility. This divergence highlights a critical point in the narrative. Bipedalism alone did not determine the future of the human lineage. It was a necessary foundation, but not a sufficient explanation for later success. From an evolutionary perspective, Paranthropus represents a side branch rather than a direct ancestor of modern humans, but it is a vital side branch. It shows that walking on two legs did not automatically lead to larger brains, advanced tools, or global dispersal. It also underscores how evolution works through branching, not ladders. At any given time, multiple hominin species could exist, each adapted to slightly different ecological niches, all sharing a common mode of locomotion. The robust hominins also help us understand why bipedalism endured. Even in a lineage focused on chewing rather than moving, upright walking remained advantageous. It continued to support foraging, carrying, and efficient ground travel, regardless of dietary emphasis. With the appearance of the genus Homo, bipedalism enters a new phase. Upright walking is no longer just a way to move between nearby food patches or balance life between trees and ground. It becomes the foundation for a broader lifestyle defined by mobility, planning, and expanding horizons. The earliest members of Homo appear in Africa roughly 2,400,000 years BCE. Their exact classification remains debated, but fossils often assigned to Homo habilis and closely related forms mark a clear shift in anatomy and behavior. These hominins were still recognizably bipedal, but their bodies were beginning to change in ways that reflect new demands placed on walking. One of the most important changes involves body proportions. Compared to Australopithecus, early Homo shows a gradual increase in leg length relative to arm length. Longer legs improve stride length and reduce the energy cost of walking over distance. This is a subtle change, but its consequences are profound. It signals a shift toward covering more ground as a routine part of daily life. This does not mean early Homo immediately became endurance walkers or travelers across vast territories, but it does suggest that selection was now favoring individuals who could move efficiently between more widely spaced resources. In a landscape where food availability was unpredictable, the ability to travel farther could make the difference between survival and starvation. The pelvis also continues to change. While still broader than that of modern humans, the pelvic structure in early Homo supports more efficient weight transfer during walking. Combined with changes in the lower spine, this anatomy allows for a more stable and sustained upright posture. Feet show further refinement as well. Although not yet fully modern, early Homo feet appear more rigid than those of Australopithecus. Increased rigidity improves push-off during walking, making each step more efficient. Over long distances, even small improvements in efficiency reduce fatigue and conserve energy. These changes indicate that walking itself was becoming more central to hominin life. Upright movement was no longer just habitual, it was becoming optimized. This shift in locomotion coincides with changes in behavior. Early Homo is associated with the earliest widely accepted stone tools, often referred to as Oldowan tools. These simple flakes and cores were used for cutting, scraping, and pounding. While tool use is not the focus of this section, it matters here because tools and walking are linked. Stone tools are heavy. Carrying them requires free hands and a stable walking posture. Early Homo individuals who could transport tools between locations had access to resources that others did not. This includes cutting meat from carcasses, processing plant materials, and accessing marrow from bones. The need to carry tools, food, or both reinforces selection for efficient bipedalism. Walking becomes not just a means of getting from place to place, but a way to connect activities across space and time. Dietary evidence suggests that early Homo consumed more animal protein than Australopithecus, though still as part of a mixed diet. Accessing animal resources often requires travelling to carcasses, returning to safe locations, and sometimes competing with other scavengers. Upright walking supports all of these behaviours by enabling transport and improved visibility. This increased reliance on mobility changes how hominins interact with their environment. Instead of exploiting a small home range intensively, early Homo likely used larger territories more extensively. This pattern favours walking that is sustainable rather than merely functional. Social organisation may also have shifted as a result. Moving across larger areas increases the importance of group coordination. Individuals who can keep pace, carry resources, and navigate terrain effectively contribute more to group success. Over time, selection favours bodies that support these roles. Importantly, these changes occur without dramatic increases in brain size. Early Homo brains are slightly larger than those of Australopithecus, but not by a large margin. This reinforces a recurring theme. Bipedalism and increased mobility did not depend on advanced intelligence. Instead, changes in body form enabled new behaviours, which would later support cognitive expansion. The emergence of Homo also marks a narrowing of evolutionary options. While Paranthropus pursued dietary specialization, Homo leaned into flexibility. Upright walking became part of a strategy focused on adaptability rather than strength or specialization. From an evolutionary perspective, this represents a shift in emphasis rather than direction. Bipedalism remains central, but its role changes. It is no longer just about moving efficiently on the ground. It becomes a tool for connecting places, resources, and behaviors into a larger system. This is why the appearance of Homo matters so much for the story of walking on two legs. It shows that once bipedalism was refined enough, it could support entirely new ways of living. The same basic adaptation that allowed Australopithecus to forage locally now allowed Homo to think in terms of distance and movement. By the time early members of the genus Homo were moving more efficiently across the landscape, bipedalism took on a new meaning. Walking on two legs was no longer important only for travel. It now supported a deeper transformation in how hominins interacted with their world. The key to this shift lay not in the feet or legs, but in the hands. Bipedalism freed the hands from the demands of locomotion. This simple anatomical fact had far-reaching consequences, but those consequences unfolded gradually. Early hominins did not instantly begin crafting complex tools or reshaping their environments. Instead, the liberation of the hands created opportunities that natural selection would increasingly favour over time. Stone tools appear sporadically before the emergence of Homo, but with early Homo they become more common and more clearly integrated into daily life. These tools were simple by later standards. Sharp flakes struck from stone cores, used for cutting meat, scraping hides, or processing plant material. Yet even these basic tools changed the logic of survival. Using tools effectively requires carrying them. A sharp stone left behind at a quarry or riverbank is useful only once. A sharp stone carried across the landscape becomes a reusable resource. Upright walking made this possible. Individuals could transport tools from where they were made to where they were needed, linking distant locations into a single behavioral system. This connection between movement and manipulation marks a turning point. Bipedalism was no longer just about getting the body from place to place. It became part of a larger strategy that connected foresight, planning, and physical skill. Hands themselves were changing during this period. While early Homo hands were not yet fully modern, they show increasing precision compared to those of Australopithecus. The thumb becomes more robust relative to the fingers, improving grip strength and control. Wrist joints become more stable in positions useful for forceful manipulation. These changes did not happen because early Homo had suddenly become smarter. Instead, selection favoured individuals whose anatomy supported behaviours that were already proving useful. Upright walking allowed tools to be carried. Tool use rewarded hands capable of better control. Over time, anatomy followed behaviour. Cause and effect reinforce each other here. Bipedalism freed the hands. Freed hands made tools more valuable. Tools in turn made efficient walking even more important, because resources could now be exploited across larger areas. The entire system became self-reinforcing. Carrying was not limited to tools. Food transport also increased in importance. Meat, marrow-rich bones, and gathered plant foods could be moved away from dangerous or competitive locations. This allowed consumption in safer areas and may have reduced direct conflict at feeding sites. Such behaviour also has social implications. Carrying food supports sharing, whether intentional or incidental. While there is no direct evidence of structured sharing norms at this stage, repeated transport of resources changes how individuals relate to one another. It creates opportunities for cooperation, tolerance, and social learning. Standing upright also improves the ability to use tools effectively. Balance matters when striking stone or cutting flesh. A stable, upright posture allows force to be directed through the arms without destabilizing the body. Over time, this mechanical advantage would favor refinements in both posture and hand use. It is important to avoid a common misunderstanding here. Bipedalism did not evolve for tool use. Upright walking appeared long before systematic tool-making. But once tools became part of hominin life, bipedalism gained new importance. What began as a solution to movement and foraging challenges became a platform for technological behaviour. This shift also affects how hominins interacted with time. Tool use encourages planning. A stone tool carried today may be used hours or days later. This introduces a new relationship between present action and future benefit. Walking, carrying, and planning become linked. Archaeological sites associated with early Homo often show repeated use over time. Stone tools accumulate, bones show cut marks, and patterns of activity suggest that certain locations were revisited. Efficient bipedal walking would have supported this kind of spatial memory and repeated movement across familiar routes. Another subtle consequence involves learning. Tool use is not entirely instinctive. It requires observation, practice, and imitation. Upright posture allows hands to be seen clearly by others, making demonstration easier. A juvenile watching an adult strike a stone core or cut a carcass can more easily copy those actions when they are performed in front of the body. This visual clarity may seem minor, but over generations it supports the transmission of skills. Bipedalism thus contributes indirectly to cultural continuity, long before culture becomes recognizable in a modern sense. With the emergence of Homo erectus, bipedalism reaches a level of refinement never seen before. Upright walking is no longer merely functional or habitual. It becomes efficient, resilient, and capable of supporting life over vast distances. This is the moment when the human body truly commits to the ground. Homo erectus appears in Africa roughly 1,900,000 years BCE and persists for well over 1,000,000 years. Fossils attributed to closely related forms, sometimes called Homo ergaster in Africa, show remarkable consistency in body design across time and geography. This consistency tells us something important. Natural selection had arrived at a body plan that worked extremely well. The most striking change lies in overall proportions. Homo erectus had longer legs and shorter arms relative to body size than any earlier hominin. This shift dramatically improved walking efficiency. Longer legs increase stride length, allowing more ground to be covered with fewer steps. Over long distances, this reduces energy expenditure and mechanical stress. This was not a small adjustment. It represented a fundamental redesign of the hominin body around terrestrial movement. The pelvis of Homo erectus is narrower and more modern in shape than that of Australopithecus. This structure supports a more stable trunk during walking and allows for smoother weight transfer from one step to the next. Combined with changes in the lower spine, it enables an upright posture that can be maintained for hours rather than minutes. The knee joint also shows important refinements. Homo erectus knees are capable of locking fully during the stance phase of walking, reducing the muscular effort required to stay upright. This feature allows individuals to stand and walk with less fatigue, a critical advantage for long-distance travel. The foot completes this transformation. Fossil evidence shows a fully developed longitudinal arch, which acts like a spring. With each step, energy is stored and released, making walking more efficient and less taxing. The toes are shorter and aligned, improving balance and push-off. The foot is no longer a compromise between climbing and walking. It is a dedicated walking structure. Taken together, these changes produce a bipedal gait that is fundamentally modern in its mechanics. Homo erectus still differs from modern humans in some details, but the core system is in place. Walking is now cheap, stable, and sustainable. This matters because it changes what hominins can do. Homo erectus was the first hominin to expand far beyond Africa. Fossils appear across parts of Asia and possibly Europe, indicating movement across thousands of kilometers. Such dispersal would have been impossible without highly efficient bipedal locomotion. Walking long distances is not just about reaching new places, it is about surviving once you get there. Efficient walking allows individuals to patrol large territories, track seasonal resources, and return reliably to water sources. It supports exploration without catastrophic energy loss. Environmental context helps explain why this mattered. During the time of Homo erectus, climates continued to fluctuate. Open landscapes expanded in many regions, and resources were often widely spaced. A body built for endurance walking was perfectly suited to these conditions. Homo erectus anatomy also suggests a new relationship with time. Long-distance walking encourages planning. Individuals must anticipate water availability, shelter, and food over the course of a day or longer. While we must be cautious about inferring cognition directly from bones, the physical capacity for extended travel creates selective pressure for behaviors that support it. This body was not built for speed in short bursts. It was built for persistence. Homo erectus could move steadily for hours, covering ground that earlier hominins would have found exhausting. This endurance capacity would later support behaviors such as persistence hunting and long-range foraging, even if those behaviors were not yet fully developed. Another important feature is body size. Homo erectus was taller and heavier than Australopithecus, with body proportions closer to modern humans. Larger size increases stride length and improves thermoregulation, especially in open environments. Combined with upright posture, it reduces heat gain from direct sunlight and improves cooling through airflow. Thermoregulation becomes especially important once hominins begin traveling in open landscapes during the heat of the day. Efficient walking and effective cooling work together, allowing movement when other predators are forced to rest. The success of Homo erectus is evident in its longevity. This species, or species complex, survived for an extraordinary span of time. Such persistence suggests that its adaptations were not fragile. They were robust solutions to the challenges of a variable world. Crucially, bipedalism is no longer under question or experimentation at this stage. There is no competing locomotor strategy within Homo erectus. Climbing adaptations are greatly reduced. The upper body is no longer shaped for regular arboreal movement. Life in the trees has become peripheral, not central. This represents a decisive shift. Earlier hominins balanced ground and tree. Homo erectus commits to the ground. That commitment reshapes everything else. Carrying becomes routine. Tools can be transported over long distances. Food can be moved from kill or gathering sites to safe locations. Groups can remain cohesive while ranging widely. By the time Homo erectus was walking efficiently across open landscapes, a long-standing balance finally tipped. For millions of years, hominins had lived between trees and ground, maintaining climbing abilities alongside upright walking. Now, for the first time, life on the ground offered more advantages than life in the branches. This was not a sudden decision, but the outcome of accumulating pressures that made climbing increasingly unnecessary and eventually costly. The world Homo erectus inhabited was different from that of earlier hominins. Open environments expanded across large parts of Africa and beyond. Forests did not disappear, but they became more fragmented and less central to daily survival. Resources such as water, plant foods, and animal carcasses were often spread across wide areas, favoring those who could move efficiently over long distances. In this context, climbing became less valuable. Trees still provided shade and occasional food, but they were no longer the primary source of safety or sustenance. Predation pressures also changed. Larger body size, group living, and improved visibility reduced reliance on trees as escape routes. Instead of fleeing upward, hominins increasingly relied on early detection, coordinated movement, and endurance to manage danger. The anatomy of Homo erectus reflects this shift clearly. Upper bodies lose many climbing adaptations seen in Australopithecus. Shoulders are positioned lower and oriented more toward manipulation than suspension. Arms are shorter relative to legs, reducing climbing efficiency but improving balance and endurance during walking. Hands become less suited for grasping branches and more adapted for carrying and tool use. These changes are not neutral. A body optimized for walking is a body that has given up something else. Climbing with shorter arms, stiffer shoulders, and altered wrists is harder and more dangerous. Once these traits spread through a population, returning to a tree-based lifestyle becomes unlikely. This is how evolutionary commitments work. Selection does not just favor new traits, it also removes old options. Ground living also offered new rewards. Traveling long distances made it possible to track seasonal resources, revisit productive locations, and exploit environments that were inaccessible to less mobile species. Homo erectus could range widely without exhausting itself, a decisive advantage in unpredictable climates. Water access is a crucial part of this story. As hominins moved into drier and more open regions, reliable water sources became central to survival. Efficient walking allowed groups to plan movements around rivers, lakes, and seasonal water holes. Climbing offered no comparable advantage here. Another factor is energy economics. Climbing is energetically expensive, especially for larger bodies. As hominins grew taller and heavier, the cost of climbing increased. Walking, by contrast, became cheaper as anatomy improved. Once the energy balance favored walking, selection reinforced terrestrial life. Social behavior reinforced this trend. Group movement across open ground encourages cohesion and coordination. Individuals who could keep pace contributed to group success. Those who lagged behind faced greater risk. Over generations, this dynamic favored bodies built for sustained walking rather than vertical escape. Sleeping behavior likely changed as well. While earlier hominins may have slept in trees to avoid predators, larger-bodied Homo erectus groups may have begun using ground-based sleeping sites, possibly with simple shelters or controlled use of fire later on. Ground sleeping reduces the need for climbing strength and further weakens selection for arboreal traits. Importantly, this shift did not happen because trees suddenly became useless. It happened because walking became extraordinarily useful. When one strategy consistently outperforms another, evolution follows. This transition marks a psychological as well as physical boundary in human evolution. Hominins were no longer creatures of the forest edge. They became animals of the open landscape, navigating space horizontally rather than vertically. The ground was no longer a dangerous zone to cross between trees. It was home. Once hominins committed fully to life on the ground, walking on two legs took on another critical role. It was no longer only about movement or distance. It became a tool for managing heat, conserving water, and organizing daily life around time itself. In open environments, these factors can mean the difference between survival and death. As Homo erectus spread into more open and often hotter landscapes, the challenge of heat became unavoidable. Large mammals generate heat simply by moving. If that heat cannot be released efficiently, physical activity becomes dangerous. For a ground-dwelling primate without fur suited to insulation or shade from dense forests, overheating posed a serious risk. Bipedal posture offered an important advantage in this context. Standing upright reduces the amount of the body directly exposed to overhead sunlight. Compared to a four-legged animal, a biped presents a smaller surface area to the sun at midday, when heat is most intense. This does not eliminate heat stress, but it reduces the thermal load during long periods of walking. Upright posture also raises the body higher above the ground, where air temperature can be slightly cooler and airflow more consistent. Breezes at chest and head height increase heat loss through convection. Over hours of movement, even modest improvements in cooling efficiency can significantly extend safe activity time. Sweating becomes part of this system as well. While the exact timing of extensive sweat gland development is debated, humans today rely heavily on sweating to regulate body temperature. Efficient walking posture works in concert with sweating by allowing continuous movement without rapid overheating. An upright walker can maintain a steady pace while dissipating heat, rather than being forced to stop frequently. Water management is closely tied to heat regulation. Sweating and breathing increase water loss, making access to water sources critical. Efficient bipedal walking allows hominins to plan movements around rivers, lakes, and seasonal waterholes. The ability to travel between water sources without exhausting energy reserves or overheating would have been a major selective advantage. This planning introduces a new relationship with time. Walking long distances in hot environments requires careful timing. Movement during cooler parts of the day reduces heat stress and water loss. Efficient bipedalism makes this possible by lowering the energy cost of sustained walking, allowing hominins to travel early in the morning or later in the afternoon without fatigue. In contrast, many large predators are forced to rest during the hottest hours. This creates a temporal niche. Hominins capable of walking steadily in warm conditions could move when competitors could not. This does not require speed or aggression. It requires endurance and thermal tolerance. The relationship between bipedalism and time also affects foraging. Ground-based resources such as tubers, seeds, and carcasses may be available at specific times or places. Efficient walking allows individuals to arrive when conditions are favorable and leave before heat becomes dangerous. Over generations, this reinforces selection for bodies that can manage both distance and duration. Another important factor is water transport. Carrying water is only possible with free hands and stable walking posture. Even simple containers made from natural materials would allow hominins to extend their range beyond immediate water sources. While direct evidence for water containers appears much later, the physical capacity to carry water begins here. Heat management also interacts with body proportions. Homo erectus had longer limbs and a more linear body shape than earlier hominins. Such proportions increase surface area relative to body mass, aiding heat dissipation. Combined with upright posture, this body form is well suited to warm, open environments. These traits are not accidental. They reflect selection acting on the entire body as a system. Walking posture, limb length, body shape, and skin physiology all interact to manage heat and water balance. Time management extends beyond daily movement. Seasonal planning becomes more important in open environments. Efficient walking allows groups to track seasonal changes in resource availability, moving toward water and food as conditions shift. This mobility reduces dependence on any single location and buffers against local shortages. This does not require complex abstract thinking. It requires bodies capable of following opportunities across space and time. Bipedalism provides that capacity. By the time bipedal walking was fully refined, the human body possessed a remarkable foundation. Upright posture, efficient strides, and effective heat management had turned walking into a powerful survival tool. From this foundation, a new possibility emerged. Hominins were not only capable of walking long distances, they were also becoming capable of sustained running. This development did not replace walking. Walking remained the core mode of movement. Running added a new layer, extending what bipedalism could do under certain conditions. Understanding this transition reveals how walking on two legs became a platform for entirely new behaviors. Running is fundamentally different from walking. It places greater stress on joints, muscles, and connective tissues. It generates far more heat and demands more energy. For most animals, running is reserved for short bursts, usually to escape predators or capture prey. Sustained running is rare among mammals, yet humans are unusual. Compared to other primates, and even many quadrupeds, humans are exceptionally good at endurance running. This ability did not appear suddenly. It grew out of the same anatomical changes that made walking efficient. Several features that evolve for walking also support running. Long legs increase stride length, reducing the number of steps needed to cover distance. Strong hip muscles stabilize the trunk during rapid movement. A narrow waist allows the upper body to rotate independently of the hips, improving balance. The spring-like arch of the foot stores and releases energy with each stride. Perhaps most importantly, upright posture combined with effective cooling allows movement to continue without dangerous overheating. Running generates heat rapidly, but an upright body with efficient sweating can shed that heat more effectively than a fur-covered quadruped relying on panting. These traits are clearly present in Homo erectus and later hominins. While we cannot observe their behavior directly, their anatomy suggests that sustained running was at least possible. Whether it was regularly practiced remains debated, but the capacity itself is significant. Why would this capacity matter? One possibility is persistence hunting. This strategy involves tracking prey over long distances until it overheats and collapses. Humans do not outrun prey in speed, they outlast it in endurance. In hot environments, this strategy can be effective, especially when combined with cooperation and tracking skills. Even if persistence hunting was not widespread early on, the ability to run for extended periods would have had other uses. Chasing wounded animals, traveling quickly between distant locations, or responding to sudden opportunities all benefit from sustained running ability. Running also changes predator interactions. While hominins were not faster than many predators, the ability to move steadily over long distances could help escape threats by maintaining separation rather than relying on sudden bursts. Endurance can be as effective as speed. It is important to emphasize that running did not drive the evolution of bipedalism. Walking came first, and running emerged later as a secondary benefit. The body was not built to run, and then adapted for walking. It was built to walk, and that walking body happened to be capable of running. This distinction matters for understanding causality. Bipedalism did not evolve because it enabled running. Running became possible because bipedalism was refined to a high degree. From an evolutionary perspective, this represents an expansion rather than a redirection. The same anatomical system supports both behaviors, but walking remains dominant. Running is situational, used when the benefits outweigh the costs. The ability to switch between walking and running adds flexibility. Hominins could walk efficiently for most of the day, conserving energy, and run when necessary to seize an opportunity or respond to danger. This combination is rare in the animal kingdom and reflects a highly adaptable locomotor system. running also places new demands on coordination and balance. Maintaining stability at higher speeds requires precise control of posture and limb movement. This likely reinforced selection for neurological control and musculoskeletal resilience, further refining the bipedal system. Another important factor is group behavior. Sustained running becomes more effective when done cooperatively. Tracking an animal, sharing the effort, and coordinating movement over long distances all benefit from social cooperation. While direct evidence is limited, the physical capacity for endurance running supports these possibilities. Heat again plays a central role. Many quadrupeds are forced to stop running once their body temperature rises too high. Humans, by contrast, can continue moving at a steady pace while dissipating heat. This advantage exists only because upright walking and running are integrated with effective cooling. It is also worth noting what running did not immediately produce. It did not turn hominins into predators dominating their environment. It did not eliminate risk or guarantee food. It simply expanded the range of strategies available. Once hominins possessed a body capable of efficient walking and occasional sustained running, the limits of movement expanded dramatically. The story now moves beyond Africa and beyond a single type of landscape. As fully bipedal humans spread into new regions, upright walking proved not only durable but adaptable, capable of functioning across a wide range of terrains and climates. This phase marks a shift from perfecting bipedalism to testing it. Forest edges, grasslands, river valleys, volcanic plains, coastlines, and eventually colder regions all place different demands on bodies moving on two legs. What is striking is not how much the human walking system changed, but how well it held together under these new conditions. As Homo erectus and later hominins expanded beyond Africa, they encountered environments unlike those of their evolutionary past. In parts of Eurasia, dense forest returned as dominant ecosystems. In others, open steppe and seasonal cold became defining features. Mountains, rocky ground, snow, and uneven terrain posed challenges very different from those of African savannas. Yet bipedalism persisted. This persistence tells us something important. Upright walking had become a general solution rather than a specialized one. It was no longer tightly bound to a particular habitat. Instead, it functioned as a flexible platform that could be adjusted through subtle changes in body proportions, muscle strength, and behavior. Fossil evidence from later hominins, often grouped under names such as Homo heidelbergensis, shows bodies that remain fully bipedal but differ in robustness. Some populations developed thicker bones and more powerful muscles, likely in response to colder climates and higher physical demands. Others retained more slender builds suited to long-distance travel. These differences reflect tuning, not redesign. The basic mechanics of walking did not change. The pelvis, knee, foot, and spine retained the core features established earlier. What changed was emphasis: strength versus endurance, insulation versus heat dissipation, stability versus flexibility. Foot anatomy provides a useful example. While the fundamental structure remained consistent, populations in colder regions may have benefited from broader feet for stability on uneven or slippery surfaces. In warmer regions, narrower feet and lighter builds reduced energy costs and heat retention. These are adjustments within a bipedal framework, not departures from it. Walking on two legs also proved compatible with new forms of clothing and equipment. While direct evidence for early clothing is limited, the ability to carry materials, wrap the body, and use simple footwear would have interacted closely with upright posture. Quadrupedal movement would make such solutions awkward or impossible. Bipedalism made them natural extensions of daily life. Terrain also shaped how groups moved together. In open areas, upright posture improved visibility and coordination. In forests, it allowed individuals to step over obstacles, carry loads, and navigate narrow paths. On rocky ground, balancing on two legs with flexible ankles proved effective. On slopes, upright walking allowed weight to be shifted efficiently uphill or downhill. One of the most important consequences of this expansion is that bipedalism became a constant across diversity. Different hominin species and populations varied in size, shape, and behavior, but all shared upright walking as a defining trait. This continuity suggests that the advantages of bipedalism outweighed its costs in nearly every environment encountered. Those costs did not disappear. Walking upright places stress on the lower back, hips, knees, and feet. Uneven terrain increases the risk of injury. Cold environments increase the energy cost of movement. Yet none of these challenges were severe enough to favour a return to quadrupedalism. Instead, solutions emerged within the bipedal system. Stronger muscles, altered gait patterns, seasonal movement strategies, and social cooperation all helped manage risk. Injured individuals could be supported by groups. Knowledge of terrain could be shared. Paths could be reused. This social dimension matters. Walking into new worlds was not an individual achievement. It was a group process. Efficient bipedalism allowed groups to stay together while moving, maintaining communication and shared purpose across long distances. The archaeological record supports this picture. Sites across different regions show repeated occupation, suggesting that groups returned to familiar places rather than the Wyoming dust. Owen was smooth and calculating in his expensive suit and polished boots, a man who had grown wealthy foreclosing on desperate ranchers and acquiring their land piece by piece, and he held Jake's mortgage along with the cavalry contract that represented the difference between survival and total ruin. He claimed he had come to check on Jake's progress with the Mustangs, but Elizabeth could see the predatory gleam in his pale eyes as he surveyed the property, already counting the value of prime water rights that would be his when Jake inevitably failed. Catherine stepped down from the buggy with elaborate care to avoid soiling her silk skirts, her gaze sweeping over Elizabeth with thinly veiled contempt before she delivered her barb in a voice like honey over poison, remarking how quaint it was that Jake had acquired a mail-order bride who was playing at being a field hand. Elizabeth met her stare without flinching and said nothing, knowing that women like Catherine Hartley fed on reactions and would find no satisfaction in silence. Owen examined the still wild Mustangs with theatrical concern, noting aloud that the deadline was now only 5 weeks away, and the horses appeared no closer to being broke than when Jake had acquired them 3 months prior. Perhaps Jake should consider his generous offer to purchase the ranch outright before foreclosure proceedings became necessary and even more unpleasant. Jake's face went hard as stone, but he kept his voice level, as he assured Owen that the contract would be fulfilled, and the mortgage payments would resume once the cavalry paid for delivery. But Elizabeth could see the desperation beneath his false confidence, could see how his hands clenched and unclenched at his sides. After Owen and Catherine departed in their fine buggy trailing dust and implied threats, Jake walked to the corral and smashed his fist into a fence post with such violence that Elizabeth heard the wood crack, and she watched him stand there breathing hard and bleeding from split knuckles while the Mustangs screamed their usual panic at the edge of the enclosure. She made her decision in that moment, walking across the yard to where he stood, radiating frustration and fear, and she said quietly that she wanted to try working with the horses. Jake laughed, a bitter sound without humour, asking if she truly believed that she as a woman could succeed where he and his experienced ranch hands had failed for months. Elizabeth met his skepticism with calm directness and asked what exactly he had to lose by letting her try, the question hanging between them like a challenge and an offer simultaneously. Jake stared at her for a long moment, his grey eyes searching her face for mockery or delusion, and she held his gaze steadily, until finally he said, She could have 2 weeks. If she could not show measurable progress, by then she would stop this foolishness and leave the horses to him. Elizabeth nodded once in bones suited to bearing heavy loads and absorbing impact on hard or uneven ground. Modern humans tend to have lighter feet with more pronounced arches, improving efficiency during long-distance walking and running. Despite these differences, the basic walking pattern remained the same. Heel strike, weight transfer, and push-off occur in both groups. The spine curves, pelvis shape, and knee alignment all reflect a shared evolutionary heritage. This shared heritage is important because it shows how deeply fixed bipedalism had become. Even as humans adapted to radically different environments, the core system of upright walking remained unchanged. The archaeological record supports this continuity. Neanderthals and modern humans left footprints, trackways, and activity sites that show similar movement patterns. They travelled across landscapes, revisited locations, and organised their lives around walking-based mobility. What differs is how movement fit into broader survival strategies. Neanderthals appear to have relied heavily on close-range hunting of large animals. This strategy demands strength, coordination, and resilience. Walking for Neanderthals was not primarily about covering vast distances quickly. It was about positioning, persistence in harsh conditions, and transporting heavy carcasses or materials. Modern humans, especially after expanding into new regions, often relied on more varied subsistence strategies. Long-distance travel, flexible foraging, and extensive social networks became increasingly important. Efficient walking supported these behaviors by reducing the cost of movement and enabling wider exploration. After millions of years of gradual change, experimentation, and refinement, walking on 2 legs became one of the most consequential adaptations in human history. By the time anatomically modern humans appear, bipedalism is no longer evolving in any fundamental way. It is complete. What remains is its legacy, a balance sheet of gains and costs that continues to shape human life today. To understand why bipedalism matters so deeply, it helps to step back and view it not as a single trait, but as a reorganization of the entire body and way of life. Walking upright altered how humans moved, how they used their hands, how they managed energy, and how they interacted with one another and the environment. In doing so, it made later developments possible, but it also imposed limits that we still live with. The benefits are clear and far-reaching. Bipedalism freed the hands permanently. This allowed humans to carry food, tools, infants, and eventually cultural objects. Without this freedom, sustained tool use and cumulative technology would have been impossible. Even the most sophisticated tool traditions depend on the simple fact that the hands are not required for locomotion. Upright walking also made long-distance travel efficient. Humans became animals of movement, capable of crossing landscapes, tracking resources, and dispersing into nearly every environment on Earth. This mobility supported exploration, migration, and social connection across distance. It turned geography from a barrier into a network. Energy efficiency is another major gain. Compared to many forms of quadrupedal movement, human walking is remarkably economical over long distances. This efficiency allowed our ancestors to forage widely without exhausting themselves, supporting flexible diets and resilience in unpredictable environments. Heat management further amplified this advantage. Upright posture, combined with sweating and reduced body hair, allowed humans to remain active in conditions that forced many predators and competitors to rest. This opened temporal opportunities, letting humans move, forage, and hunt when others could not. Bipedalism also reshaped perception. Standing upright raises the head, extending visual range and improving awareness of surroundings. This mattered for detecting threats, locating resources, and coordinating group movement. Over time, it likely influenced communication, gesture, and social signaling. Taken together, these benefits made humans exceptionally adaptable. They did not specialize narrowly in one habitat or food source. Instead, they specialized in flexibility itself. Bipedalism was the physical foundation of that flexibility. But this foundation came at a price. Walking upright places enormous stress on the skeleton. The human spine, adapted from a structure once used primarily in horizontal posture, now bears vertical loads. This makes it vulnerable. Lower back pain, spinal disc problems, and posture-related injuries are not modern anomalies. They are structural consequences of bipedalism. The hips and knees also pay a cost. Supporting body weight on two legs concentrates force on fewer joints. Over time, this leads to wear, arthritis, and reduced mobility. These issues appear even in physically active populations and are visible in skeletal remains from the deep past. The feet, transformed into rigid levers for walking, lose much of the flexibility seen in other primates. While this improves efficiency, it increases susceptibility to injury. Stress fractures, flat arches, and joint degeneration are all part of the bipedal trade-off. Perhaps the most profound cost involves childbirth. Upright walking reshaped the pelvis, narrowing the birth canal to support efficient locomotion. Later increases in brain size enlarged the infant head. The result is an evolutionary compromise that makes human childbirth unusually difficult and dangerous compared to other mammals. This is not a flaw. It is a consequence of competing demands. The pelvis must support walking and allow birth. Evolution solved this problem imperfectly, relying on social support, assistance during labor, and developmental strategies such as giving birth to relatively helpless infants. These costs highlight a central truth about evolution. Adaptations are not optimized for comfort or longevity. They are optimized for reproductive success under specific conditions. Bipedalism succeeded not because it was perfect, but because its benefits outweighed its costs. It is also important to recognize that bipedalism constrained future evolution. Once humans committed fully to upright walking, certain paths were closed. Returning to a quadrupedal lifestyle was no longer viable. Redeveloping grasping feet or climbing specialized shoulders would undermine walking efficiency. Evolution rarely reverses such deep commitments. Instead, humans solved new problems culturally rather than anatomically. Clothing compensated for cold, tools reduced physical strain, shelter replaced trees. Medicine now mitigates some of the long-term costs of bipedal posture. Culture became a way to manage biological limits. In this sense, bipedalism marks a turning point not just in anatomy, but in evolutionary strategy. It shifted the balance from physical specialization toward behavioral innovation. Once walking provided reliable access to space and resources, selection increasingly favored learning, cooperation, and cumulative knowledge. That trajectory leads directly to the modern world. Every city, road, and migration route is built around walking bodies. Even technologies that reduce walking, such as vehicles, assume upright posture and bipedal proportions. Our tools, furniture, architecture, and social spaces are designed for bodies shaped by this ancient adaptation. At the same time, many modern health challenges reflect the mismatch between bipedal bodies and modern lifestyles. Sedentary behavior, artificial surfaces, and prolonged sitting placed stresses on systems evolved for regular movement. These issues do not negate the success of bipedalism, but they remind us of its origins. Walking on two legs was not an inevitable step toward intelligence or civilization. It was a practical response to environmental challenges faced by small populations of primates in Africa. Its consequences, however, extended far beyond those origins. By standing up, our ancestors did not just change how they moved, they changed how evolution would work on them from that point forward. Bipedalism set the direction. Everything else followed.